Hi, Sridevi from AIMS University back here to teach you geometrical isomerism in cyclic compounds. Coming to the introduction, in the case of cyclic compounds, the free single bond rotation is restricted. It is therefore important to note whether the substituents are on the same side or on opposite side of the ring. Geometrical isomerism is possible in cyclic compounds too. There should be a restriction of rotation if two carbon atoms are linked with cyclic structure. For instance, we can see three stereoisomers possible for 1,2 dimethyl cyclopentane. Trans 1R2R 1,2 diethyl cyclopentane, which is on the left hand side, and trans 1s 2s 1,2 dimethyl cyclopentane on the right hand side are enantiomeric and are therefore different compounds. Due to the identical connectivity but lacking in the mirror image relationship, the cis isomer is diastereomeric to trans isomer. Coming to the third structure, cis 1,2 dimethyl cyclopentane contains a plane of symmetry. It is superimposable on its mirror image. It follows then that cis 1R 2s 12 dimethyl cyclopentane and cis 1s 2R 12 dimethyl cyclopentane are identical, and that cis 1,2 dimethyl pentane is thus a meso compound. Coming to the properties of isomers, cis and trans isomers have different physical and chemical properties. Let's see an example. Cyclic cis 1,2 dicarboxylic acid converts to its anhydride form, but the trans 1,2 dicarboxylic acid cannot give corresponding anhydride. The cyclic cis 1,2 dicarboxylic acid and the cyclic trans 1,2 dicarboxylic acid have different boiling and melting points. Geometrical isomerism in cyclohexane. While maintaining the integrity of chemical bonds, a cyclohexane conformation may be any of the several three-dimensional shapes. The internal angle of a flat regular hexagon are 120 degrees. The cyclohexane ring tends to assume certain non-planar conformation, which have all angles closer to 109 degrees, as the preferred angle between successive bonds in a carbon chain is about 109 degrees and therefore low strain energy than the flat hexagonal shape. The most important shapes are chair, half chair, boat and twisted boat. The molecule can easily switch between these conformations, and the only two forms of them, that is the chair form and twist boat form, can be isolated in pure form. Cyclohexane conformations have been extensively studied in organic chemistry because they are the classical example of conformational isomerism, and they have noticeable influence on the physical and chemical properties of cyclohexane. This is a diagram showing the changes in the conformation along with the energy. The lowest energy is observed in chair form of conformation, also in twisted boat compared to the half chair and full boat forms. Let us see an example of cis-trans cyclohexanes. The first structure is cis-1,2 dimethyl cyclohexane, where two methyl groups are on the same side. The right-hand first structure is a trans 1,2 dimethyl cyclohexane, which the methyl group is on opposite sides. The second row first structure is a cis 1,3 dimethyl cyclohexane, in which two methyl groups are on the same side, When you see the next following structure, trans 1,3 dimethyl cyclohexane, you observe there are two methyl groups which are on opposite sides. Coming to the last row, first example, that is cis 1,4 dimethyl cyclohexane, you have two methyl groups on the same side but occupying the positions 1 and 4. On the right hand side, you can see trans 1,4 dimethyl cyclohexane where two methyl groups are trans to each other. So these are all the examples for cis-trans cyclohexanes. Coming to the other example of dichlorocyclohexanes. There are three examples here: cis 1,2 dichlorocyclohexane, cis 1,3 dichlorocyclohexane and trans 1,2 dichlorocyclohexane. All these also come under geometrical isomerism of cycloalkanes. In cis 1,2 dichlorocyclohexane, both the chlorines are in axial position. In trans 1,2 dichlorocyclohexane, we have the chlorine atoms, one in axial position, the other in equatorial position. In cis 1,3 dichlorocyclohexane, we have both the chlorine atoms in equatorial position. So, if both chlorine atoms in axial position or both chlorine atoms in equatorial position, we call them as cis. So, one chlorine in equatorial position, the other chlorine in axial position, we call that condition as transposition or trans isomer. Here we end our topic, the geometrical isomerism in cyclic compounds. Thank you so much.